I brought in all these clips together to show you all these different storm systems, starting with a hurricane. This is a computer graphic showing the Coriolis effect. It rotates counterclockwise. This is a tornado. These are all clips from North American storms. It is rotating counterclockwise. That's from the Coriolis effect. This one's pretty easy to see that it's rotating counterclockwise. That's the opposite direction from the clock direction. This is a twister, and it's a little bit harder to see this one, but it is rotating counterclockwise. These are all North American storms. In South America, it's the opposite direction. I will explain how that happens later on. This fellow is out there in the field gesturing. He's showing you, again, this counterclockwise rotation. This is another twister in North America. Cyclones, hurricanes, tornadoes, they're all going to be having this Coriolis effect. In North America, they rotate counterclockwise. This one's pushing up across Florida, and you can see quite clearly it's counterclockwise. So we'll talk a little bit about how this happens. Now I have a really good way to explain how this Coriolis effect happens, and it involves using a balloon. So I have a balloon here. Now you guys can get a balloon and follow along and try this. It's actually very simple. You're probably wondering, what in the world can we do with a balloon to show this Coriolis effect, which is kind of mysterious. I get it. But first, I'm going to walk you through this lab sheet that we use when you come up into the science lab to talk about the Coriolis effect. The first question on the lab sheet asks you, the Earth rotates from blank to blank. Which way does the Earth rotate? All these things come together to make this Coriolis effect happen. So which way does the Earth rotate? Now pretend that this is the Earth, okay, and you've got the North Pole up here. I'm just going to mark an N to show this is the North Pole. Down here, the really weird nub of the balloon, that's the South Pole. So if this is the Earth and you're standing on the Earth, which way does it rotate? Does it rotate from east to west, or does it rotate from west to east? Which way does it turn? I mean, it turns one way and not the other, and that's the way it's always been. So which way does it go? All right, now think about this. If you're standing on the Earth, okay, this is you standing on the Earth, and you're aware of sunrise and sunset, okay, which way does sunrise come? Which way does sunset go? What's the direction for everything? It depends on which way the Earth is turning. So you're standing on the Earth, sunrise comes this way, right? They say the sun rises in the east and sets in the west. So that means if the sun is out there in space and you see it rising in the east, that means the Earth is turning from west to east. Does that make sense? I mean, think about it. That sunrise, it's going to show up in the east. Sunset, let's say the sun is, out there in space, and now it's the end of the day and you're standing on the Earth, and sunset is happening in the west, right? Sunset, that's the west, and the sun is setting in that direction. That means the Earth is turning this way, from west to east, okay? So the Earth is turning from west to east. So here's what we're going to do to help us remember that. We're going to mark on the balloon a line to show a little bit like something like the horizon. It's not a perfect straight line, and it's not perfectly bisecting the planet. That's your horizon, and we're going to turn this into an arrow to show that the Earth is turning west to east. This is the west, north, west, east, south. So the Earth is turning from the west to the east. So the Earth is always turning in this direction, and it turns once every 24 hours. That's a day. Okay. The next thing on the lab sheet is asking about the different speeds of different places on the planet. This all plays together to create this Coriolis effect, so bear with me. Now this next question says, okay, points on the Earth's surface move at different speeds. Okay, that's a fact, and as we go through this, you'll see what I'm talking about. Closer to the equator, the Earth moves more something, faster or slower, and places further away from the equator move more something, faster or slower. Okay, so now what we're going to do here is to mark a little X right here, just above the equator here, okay, and then another one up near the North Pole. That's not a Z, that's an N for North Pole, okay? there's a little mark close to the North Pole. Now, you're supposed to think about which way, which spot is moving more quickly as the Earth is turning. Okay? So here we go. Here's the Earth turning. Can you get an idea of which place is moving more quickly? Now I know you're probably thinking, well, the Earth, everything is connected to the Earth, everything's moving at the same speed. But I mean, look at this. Observe. Okay, this is science. Observe. You see the X up at the top and the X at the bottom. Okay, I'm going to go back this way. The Earth turns this way. Which X is moving more quickly? Okay, now think about it. This X is further away from the center of the Earth, and this X is very close to the center of the Earth. I mean, in terms of the axis of rotation, this is very close to that axis. This one is very far away from that axis. So, can you see that X by the equator is moving more quickly? Now think about this, okay? The Earth rotates once every day in 24 hours. This X goes all the way around. So does this one, okay? But this X is going more quickly. And how fast is it roughly going? I mean, the equator is something like 25,000 miles around. And in 24 hours, it goes all the way around. So 25,000 miles, okay, divided by 24 hours, how many miles per hour is this point moving? Okay, 25,000 divided by 24, it's roughly 1,000. It's actually more than 1,000 miles per hour this point is moving. Up here, it's going very low distance, very short distance. It's not quite that far at all. Imagine if you were standing right on the North Pole. Are you moving? You're just slowly rotating. You're just slowly rotating like this as the Earth goes around. You just go and hold the pen in the other direction. You're just doing this as the Earth goes around, okay? The whole Earth is going, and you're just going around with it once a day. You're not moving any distance at all. But here you're going 25,000 miles in 24 hours. That's 1,000 miles an hour and more, okay? This one is moving pretty fast. Now, why do we care about that? It's part of the Coriolis effect. It all adds up. There are all these different factors that add up to this Coriolis effect. Okay, now, the next question on the lab sheet that we go through, give us this idea of how all this works, is this. In a storm, low pressure air at its center pulls higher pressure air blank somewhere. I want you to think about this. So what you're going to do is this. Imagine in between these X points right here, there is a low pressure center right here. This means, of course, that there's less atmospheric pressure in this area here than all the surrounding area. And why that develops, that's a whole nother question. It's a whole nother bunch of labs experiments. But right here, let's just take for granted that there is a low pressure area right here. All around, it's higher pressure, okay? Higher atmospheric pressure all around, and right here, this is a low pressure area. This is going to be a storm. A storm is going to be happening here. Whenever there's a storm, it's because of a low pressure area. Now, what happens here is quite clearly all the high pressure area. These are H's, not 4's. That doesn't look very clear. Okay, that's a little better. Now, high pressure area is pushing inwards to this low pressure area. All this high pressure air wants to move in to that low pressure area. And you could think about it like in terms of a vacuum or a suction. Okay, this area is sucking all the air from around, and all this air is going to move in to this low pressure area. Okay, so that's what's happening there. You got all these things playing together. Rotation of the Earth, okay, what's moving faster, what's moving slower, high pressure, low pressure, all these things are coming together. We're not there yet, so don't get confused. Okay, now, the next question on the lab sheet is this. Because of the Earth's rotation, as air moves north, okay, all this area here, all this air is moving north, okay, because there's low pressure. Now this air is moving north. Now as air moves north, it gets an extra push towards the east. Why? Because the Earth is rotating this way. And so this fast-moving air, it's moving faster than air up here. It's moving faster, and it's getting a little bit of a kick to the east because of this rotation of the Earth. Everything around here is a little bit slower. This is faster. It's faster moving air. It's moving 1,000 miles an hour. And it gets a little bit of a kick towards the east because the Earth is rotating towards the east. It's launching it. Now, it's like when you guys are riding on a merry-go-round in the park, okay? And you try to throw a ball from that rotating motion there. It gets an extra kick from the direction of the rotation of the merry-go-round. It's exactly the same thing. Okay, now, as air moves south, it gets an extra push towards the west because it's moving more slowly than all the air down here. See, as we go south, air is moving faster and faster. And as we go north, air is moving slower and slower because of that rotation of the Earth. And so anything moving south, any air moving south is going to kind of be pulled a little to the west because it's moving more slowly, I should say, than the air that's further south. Okay? So this is what you're going to see there. Air moving north is going to get a bit of a kick to the east. Air moving south is getting a kick to the west. Now the last part of the lab sheet says, together these facts give us the spiraling, rotating motion of storms. That's the Coriolis effect. Now let me complete this here. You have air moving north, okay? And it's getting a bit of a kick to the east. Now is it just going to keep on going straight across the whole Earth, just like that forever and ever? Well, no, because it's going to pass this low pressure zone. What's it going to do? It's going to get sucked into this low pressure zone. And this air that's moving south, is it just going to keep going straight all the way across the whole face of the Earth? No, it's going to get pulled into this low pressure zone also. Now is that starting to look like something that we've seen over and over again? Right? This looks like that counterclockwise rotation of storms, and it's happening all across the entire face of this region. All the air is being pulled into this storm in this counterclockwise kind of a pattern. Because of the Coriolis effect, all these combined different factors, we have this counterclockwise rotation of storms, tornadoes, hurricanes, twisters, doesn't matter. They're all turning counterclockwise because of this Coriolis effect. Now, that is the northern hemisphere. You're aware of that, right? Here's the equator. We live here. This is North America. Europe is over there. This is the northern hemisphere. So that's why we're seeing this happening counterclockwise in the northern hemisphere. So how do you explain in the southern hemisphere it goes in the opposite direction? Well, it's pretty simple actually. Let's do it this way. We've got a low pressure center right here. All the air, you get the idea. It's all high pressure here. This is low pressure here. All the air around is going to get pulled into this low pressure center. Okay, it's getting pulled in, pulled in, pulled in. Now, if I have air moving from near the equator south towards this low pressure center, it's getting an extra kick to the east because of the rotation of the Earth. Right? Makes sense? So this is the faster moving point compared to down here. This is a slower moving point. All this air is moving slower than this air over here. Air that's moving north, getting sucked into this low pressure center, is going to get a bit of a pull to the west. Okay? Because this air is moving slower than all the air surrounding it. And that means that as this moves north, it's going to get sucked into that low system. And this is moving, it's not going to go, it's like before, it's not going to go straight across the Earth. No, it's getting sucked in there. And you're going to have this kind of pattern. Okay? Everything around is going to be pulled in this way, in the opposite direction. Okay? This is clockwise. Southern hemisphere systems turn clockwise because of the Coriolis effect. Northern hemisphere systems turn counterclockwise because of the Coriolis effect. So that is, in a nutshell, on a balloon, how you explain the Coriolis effect. It's a very complicated thing, and there's more to it, of course. Again, we did talk at all about how do we develop these low pressure systems, and that's a whole different thing. But that's the Coriolis effect, quite simply. And see, you can do that on a balloon. Okay, thanks for watching, you guys. Hope you enjoyed this, and we'll see you next time when we do some more science on the Science Lab. See you later.